All right, so today we're going deep on anions.
Anions.
You got anions.
Yeah.
And, these tiny little negatively charged ions are causing a big stir in the world of quantum technology.
Yeah.
Who knew?
Right.
We're going to be looking at this essay, Anionen, Schlüsselteilchen in der Quantentechnologie.
Okay.
By Jorgo Schneeppert. And just diving into how these little things could be a key ingredient in some really groundbreaking tech.
Yeah. It's wild how something so small can have such a massive impact.
I know, right?
Like, for the longest time, anions were just kind of like this basic concept in physics,
Right.
But now they're front and center in quantum tech. It's pretty amazing.
So I remember anions from way back in chem class.
Oh, yeah.
But just to refresh everyone's memory,
Sure.
What exactly makes them different from like those positively charged ions, the cations?
Okay, so think about table salt.
Okay.
Sodium chloride, right? The net, it gives up an electron, becomes a positively charged Tylage cation.
Right.
But chlorine, sleek, that guy loves to snag an extra electron and boom, turns into a negatively charged chloride anion.
Opposites attract.
Exactly.
It's all about that electron exchange.
It is.
But how do we go from like basic table salt to these crazy powerful quantum computers everyone's talking about?
Okay, so that's where things get super interesting.
Okay.
See, it's not just about the extra electron. It's about how those extra electrons behave.
Okay.
Especially when you look at them through the lens of quantum mechanics.
Quantum mechanics.
Yeah.
My head's already starting to spin a little bit.
I know it can be a bit mind-bending.
But how do scientists even like study something that small?
Well, they use these super sophisticated tools and mathematical models.
Oh, wow.
One of the big ones is the Schrödinger equation.
The Schrödinger equation.
Yeah, which basically helps describe the wave-like nature of particles like electrons.
Okay, Schrödinger equation, that one's a bit beyond me.
It's a complex.
But I guess the gist is scientists are using math to like zoom in and see how those extra electrons in the anions are zipping around.
Exactly, and what they're finding is that these electron configurations, the way those electrons are arranged, they give anions unique properties that are super valuable for building quantum technologies.
So it's like those extra electrons give anions superpowers in the quantum world.
You could say that
Schneeppert
talks about how certain anions, especially the ones called non-abelian.
Non-abelian anions?
Yeah, they have the potential to create stable and reliable qubits, which are the building blocks of quantum computers.
Non-abelian anions for qubits. That sounds pretty intense.
It is.
What makes them so special for building those qubits?
Okay, so it gets pretty complex.
Okay.
But essentially, these anions have unique quantum states that can be manipulated in ways that other particles can't.
Really?
Like, imagine being able to braid their paths in space to change the state of a qubit.
Wait, braiding anions?
Yeah.
What does that even mean?
Well, it's not braiding in the traditional sense, of course.
Oh, okay.
But the analogy helps to understand how scientists can control the state of a qubit by carefully manipulating the paths of these non-abelian anions.
So it's like each anion is a tiny little dancer.
Okay.
And scientists are like choreographing their movements to perform calculations.
Yeah, that's a great way to think about it.
It's amazing.
And remember, we're still early stages of research here.
Right.
There's so much more to learn about how to harness the power of anions for quantum computing.
This is already blowing my mind, and we're just getting started.
Yeah.
Schneeppert's essay also mentions that anions are useful for way more than just computing.
Oh, yeah, for sure.
What about quantum sensing? How do they fit into that?
Anions are super sensitive to electromagnetic fields.
Okay.
Which makes them perfect for building extremely precise sensors. Like, imagine a sensor so sensitive it can detect the faintest heartbeat of a baby still in the womb. That's the kind of power we're talking about.
That's incredible. What about quantum cryptography?
Oh, yeah.
I always hear that it could make our data, like, unhackable.
Right.
Do anions play a role there, too?
Absolutely. Anion-based methods are being explored as a way to generate and share secret keys for encryption.
Wow.
It's like using the universe's own code to protect information.
So it's incredible how these tiny little particles have the potential to revolutionize so many different fields.
It's remarkable.
Yeah.
But before we get too carried away,
it's
important to remember that working with anions at this level, it's not easy.
Right.
Schneeppert highlights some of the challenges researchers are facing.
Yeah.
Especially when it comes to stability.
Okay, so what's the catch?
Well,
I have a feeling it's not as simple as just grabbing a handful of anions and plugging them into a quantum computer.
Exactly.
Right.
Remember how we talked about those extra electrons in anions? Yeah. Well, they can be a bit finicky.
Oh.
Anions are quite sensitive to their environment. And if they bump into the wrong particle, they can recombine. And they lose those special properties that make them so valuable for quantum technology.
So it's like trying to juggle fragile snowflakes?
Yeah.
One wrong move and poof, they're gone.
Exactly. It's a constant battle to keep anions stable and prevent them from recombining.
So how are scientists tackling this challenge? Surely they're not giving up on anions just because they're a bit delicate.
Of course not. Scientists are incredibly resourceful.
Right.
They're developing innovative techniques like laser cooling.
Laser cooling?
Yeah, where lasers are used to slow down the movement of anions, making them less likely to collide and recombine.
It's like using lasers to chill out these hyperactive anions.
That's a good way to put it.
Okay.
And along with laser cooling, scientists are also using sophisticated ion traps.
Ion traps?
Yeah, these are devices that use electromagnetic fields to isolate individual ions.
Wow.
Including anions, creating a safe haven for them to do their quantum magic.
So it's like building tiny prisons for each anion, keeping them protected and ready for action.
Precisely. And the development of these increasingly sophisticated tools is essential for advancing anion-based quantum technologies.
Wow, this deep dive is already full of surprises.
Yeah.
We've gone from simple table salt to the mind-boggling world of quantum computers and beyond.
It's pretty wild.
It's clear that we've only just begun to scratch the surface of what anions can do.
Yeah, definitely.
I'm excited to see what else we uncover as we continue this deep dive.
There's so much potential with these tiny anions.
But before we are talking about the challenges of working with anions, how sensitive they are.
Yeah.
But what about the future? Where do we go from here with anions in these cutting-edge fields?
Well, one area that Schneepat really emphasizes is the development of new topological quantum materials.
Okay.
It's a fascinating concept.
Topological quantum materials, break that down for me.
Okay.
How do anions fit into all of this?
All right, so imagine a donut and a coffee cup.
Okay.
They seem different, right?
Yeah.
But topologically, they're the same.
Okay.
They both have one hole.
I see.
Now think about materials that have unique properties based on their topological structure.
Okay.
The way their atoms are arranged, not just what they're made of.
So we're not just talking about the chemical composition.
No.
But the shape and arrangement of their atoms.
Exactly. And what's incredible is that in certain materials, anions can actually create these special topological states.
Hold on. Anions can shape the topology of a material.
That's right. And these topological states are incredibly robust, resistant to disturbances.
Okay.
It's like building a quantum fortress where information can be stored and processed with incredible reliability.
Wait, so we were just talking about how difficult it is to keep anions stable.
Right.
And now we're talking about using them to create materials that are inherently stable.
Exactly.
That sounds like a game changer.
It is. Topological quantum materials have the potential to revolutionize quantum computers.
Wow.
Making them far more resilient to errors and noise. And that's just one application.
Okay.
Schneepat also discusses the potential of anion-based quantum optics.
So we're moving from rock-solid quantum computers to the world of light.
Yeah.
Quantum optics. That's pretty futuristic.
It is. Think about it. Anions are incredibly sensitive to electromagnetic fields.
Right.
That means they can interact with light at the quantum level.
Wow.
Giving us unprecedented control over photons, the fundamental particles of light.
So we could use anions to manipulate light at the smallest possible scale.
Exactly.
What would that even look like?
Imagine generating single photons on demand, perfectly controlled and ready to carry information in a quantum communication network. Or think about amplifying light signals using the quantum properties of anions.
Wow.
This is the kind of precision that could revolutionize fields like microscopy and imaging.
Okay, I'm starting to see the bigger picture here. Anions are not just about building better computers.
Right.
They could revolutionize how we communicate, how we see the world, even how we develop new materials.
You're getting it. And what's exciting is that this research is creating synergies with other fields.
Oh.
Schneepat mentions nanotechnology, for example.
Okay.
Imagine using anions as building blocks to create tiny, intricate structures with atomic precision.
Nanorobots built with anions. That sounds like something straight out of science fiction.
It does, doesn't it?
What about other areas?
Yeah.
Does Schneepat mention any other fields where anions could make a splash?
He also talks about plasma physics.
Plasma physics?
Plasmas are basically ionized gases full of charged particles. Anions with their negative charge can influence the behavior of plasmas in ways that we're just beginning to understand.
So we could use anions to control these superheated energetic plasmas.
Yeah.
What kind of applications would that have?
Think about nuclear fusion, the holy grail of clean energy. Controlling plasmas is a crucial step towards achieving sustainable fusion power, and anions could play a key role in that.
So we've gone from tiny anions to the immense power of nuclear fusion.
It is pretty incredible.
It's mind-blowing to think about the vast potential of these particles. But Schneppet's a scientist, so I'm sure he also talks about the limitations of working with anions.
Of course.
What are some of the challenges that researchers are still facing?
As we've discussed, stability is a major hurdle.
Right.
While techniques like laser cooling and ion traps have come a long way, maintaining anion stability in complex real-world systems remains a challenge. It requires ongoing research and ingenuity.
So it's a delicate balancing act, harnessing the unique properties of anions while finding ways to keep them under control.
Exactly.
What other limitations are there?
Well, the sheer complexity of working with these systems at the quantum level is another challenge. We're dealing with incredibly small scales and incredibly sensitive particles. It requires sophisticated equipment, precise control, and a deep understanding of quantum mechanics.
It sounds like we still have a lot to learn about how to manipulate anions effectively.
Absolutely. Further advancements in nanofabrication, laser technology, and quantum control methods will be essential for pushing the boundaries of what's possible with anions.
So this is a field where collaboration is key. We need experts from different disciplines, physics, chemistry, materials, science, all working together to unlock the full potential of anions.
Precisely. Schneppet emphasizes the importance of interdisciplinary research and collaboration. It's by combining expertise and perspectives that we can make the biggest breakthroughs.
Well, this deep dive into the world of anions has been an incredible journey.
It has.
We've covered a lot of ground, from the basics of these negatively charged ions to their potential to revolutionize everything from computing to medicine to energy production.
It's amazing.
And we can't forget the essay by Jürgen Schneppet, Anion, Schlüsselteil in der Quanttechnologie, which has been our guide throughout this exploration.
It's been a fascinating exploration. Anions are a perfect example of how something seemingly small can have a huge impact on the world.
And as we continue to explore the incredible potential of anions in quantum technologies, it's crucial to consider the broader implications of these advancements. What kind of future do we want to build with these powerful tools? That's a question worth pondering as we move forward into this uncharted territory.
So much potential. But we got to consider the implications, right? Like what happens when this tech really takes off?
Oh, definitely. Schneppet doesn't shy away from those potential challenges.
Yeah.
Even disruptions that anion-based quantum technologies could bring.
So let's talk about those. What are some of the things people are worried about?
Well, one of the big ones is jobs. As quantum computers become more powerful, they can start doing tasks that humans do now.
Right.
That could lead to job displacement in certain areas.
Yeah, we've seen that happen with automation before.
Exactly. It's something we need to be thinking about carefully.
So how do we prepare for that?
Well, we need to think about ways to help people adapt, like retraining programs or new educational pathways.
So it's not just about the technology itself?
Mm-hmm. It's about how we as a society adapt to it.
Right.
Does Schneppet talk about any other concerns?
Yeah, another one is inequality. Access to this tech, quantum computing and other anion-based stuff, it might not be evenly distributed.
Yeah, that makes sense.
That could make the gap between the haves and have-nots even bigger.
That's a really important point. We need to make sure these technologies are developed and used in a way that benefits everyone.
Absolutely. It's about equity, making sure everyone benefits.
So it sounds like we've got a lot to think about as we move forward with anion-based quantum technologies.
Yeah.
It's not just about the science, but the social and economic impacts too.
It's a big picture view for sure.
It's all connected.
It is.
Well, this has been an amazing deep dive into the world of anions.
I agree.
We've learned so much from those negatively charged ions to their potential in computing, medicine, energy production.
It's incredible, isn't it?
And of course, we have to thank Jürgen Schneppet and his essay, Anionen, Schlüsselteilchen, in der Quantentechnologie, for guiding us through all of this.
It's a fascinating read.
It really was. And to all of you listening out there, the future of quantum tech is still being written. Anions are just one piece of the puzzle, but a very promising one. As these technologies keep developing, We need to keep talking about these issues, asking the tough questions, and working together to shape a future where these advancements benefit all of humanity. So until next time, keep exploring and keep diving deep.